Hello students, welcome to Talk on Civil Engineering. Let us see one more example problem from losses of pre-stress in concrete in pre-stress to concrete structures. So here you have one problem stating there are it is a post tension member, okay, and there are two cables are there. So there are two cables are there, and both having an eccentricity of 100 mm below the center of velocity. Suppose so here this is a beam, and let us consider this as the center of the beam. Okay, so for this center axis, so these two cables, so he has mentioned here, here he has mentioned there are two cables are there. So these two cables are having the eccentricity of 100 at the center. Okay, and the first cable is parabolic. Is said that the first cable is parabolic and is anchored at 100 mm above the center at end. So at the end, this is having eccentricity of 100, so above above the central axis. So that means it looks something like this. Okay, so at the end also it is having 100 eccentricity. So this is the cable one. Okay, and the cable two, he said that it is a straight cable. So that means it looks something like this. So it is straight. So this is cable two. Okay, and he has given the area of the concrete section, that is AC, is equal to 2 into 10 to the power of 4, and the radius of gyration, so let us denote with r, small r, that is 120. Okay, so radius of gyration he has mentioned, and is asking to calculate what is the loss due to elastic shortening in the first cable. So when the second cable is stressed to a value of 1200 Newton per mm square, so that means he has mentioned what is the initial stress. The initial stress P naught, so P naught is equal to 1200 Newton per mm square, and he is asking to find out what is the loss due to elastic shortening in the first cable. Okay, so here it is the post tension. We know that in post tension there will be no elastic shortening loss, but there is one condition is there, that if the tendon is tensioned in stage wise, there will be a loss of elastic shortening. Okay, so here the stage wise tensioning is happened. Okay, so first initially there is the cable two is the one cable will be stressed once. After that, the second cable will be stressed. Okay, so that will be called the stage wise stressing. Okay, so the pre-stress is applied in stage wise. Okay, so this type of pre-stressing is happened. So in that case, you will have the loss due to elastic shortening as well. Okay, so since here the stage wise pre-stressing is applied, so you will have the loss due to elastic shortening as well. So we need to find out what is the loss due to this elastic shortening in first cable. That means the cable which is in the parabolic manner. Okay, and if you observe here, so he has mentioned the modular ratio as well. So let us write that value has alpha E as 6. So modulus ratio has also has given. Okay, so the one more thing, if you observe here, we don't know what is the moment of inertia of this concrete beam. Okay, I we don't know. Okay, so I we can calculate only if we know the cross section dimensions. So if it is either it is rectangular beam or I section beam, that's not mentioned here. He has not given any dimensions of the beam section. So but we need to find out I. So for that we are going to use the R value, moment of inertia and the area of concrete. So using the radius of gyration and the area of concrete, we can find out what is the moment of inertia I. Okay, so if you remember, we have a relation between I, radius of gyration, and area of concrete. So that is R, the radius of gyration, is equal to under root moment of inertia divided by A. Okay, so if you take root to that side, so it will be R square, and we need I, right? So send A to the side, so it will be A equal to I. Okay, so that means moment of inertia is equal to area of concrete into radius of gyration square. Okay, so we have all these values, just directly substitution itself. So substitute, area of concrete is 2 into 10 to the power of 4, and radius of gyration, that is 120 square. Okay, so if you calculate this, you will get the value of 288 into 10 to the power of 6 mm to the power of 4. Okay, so this is the moment of inertia. So we got moment of inertia. So you all know that we need moment of inertia to calculate FC, because so what is the formula to find out the loss due to elastic shortening? So it is alpha E into FC. Okay, so FC is the stress in concrete. So in order to find out what is the stress in concrete, so we need the moment of inertia. Okay, so now let us find out what is the stress in concrete at the center, at support and at center. Okay, FC, that is stress in concrete at the level of steel or the tendon. Okay, so at support, firstly let us find out at support. So at support and center, because at support and center you are having same eccentricity. So at center you are having 100, at the support also you are having of eccentricity of 100 itself. So for the both, for at support and center you will have the same formula, except the sign conversion, plus or minus will changes. That's it. Okay, so FC is equal to, so you have a direct stress, that is P by area of concrete. P by area of concrete. So for that we need to know the pre-stressing force, right? So did he mention the pre-stressing force? No, he has not mentioned the pre-stressing force, but he has given the pre-stressing or the initial pre-stress. So in order to find out what is the pre-stressing force, we need the area of concrete, right? So did he given the area of concrete? Sorry, area of steel. Yeah, so here he has mentioned the area of cable. So the area of cable, area of steel is equal to 100 mm square. So using this, we can find out what is the pre-stressing force, and plus or minus PE divided by I into E. Okay. So here we'll take the moment of inertia itself. Sorry, the eccentricity itself. So here E, the eccentricity is equal to my Y. So here actual in formula I'll get Y, right? The Y is the distance of from section CG of the section to the steel. The center of section to the steel distance is my Y. Okay, so here let us here my Y will be equal to E. So that is 100 mm. Okay. So this is equal to E. Okay. So firstly, let us find out what is P here. So P is equal to, so initial stress into area of steel. So initial stress is 1200 and area of steel is 100. Okay. So it will be 12 into 10 to the power of 4 kilonewtons. Sorry, newtons. So this is in Newton per mm square, right? So it will be newtons. Okay. So let us substitute the values. So 12 into 10 to the power of 4. Area of concrete is 2 into 10 to the power of 4 plus or minus 12 into 10 to the power of 4 into E is 100 and I value is 288 into 10 to the power of 6. And here my Y, the distance of tendon is equal to E. So here Y is 100. Okay. So if you calculate this value, the direct stress is 6 plus or minus, and due to eccentricity, we'll get the value of 4.2. Okay. So now what will be the stress at support and what will be the stress at center, that we need to confirm. So that can be understood by seeing the tendon profile in the beam. So this is a tendon, this is a beam, and this is the center neutral axis of the beam. So you have one cable at the bottom level and another cable parabolically provided, something like this. Okay. So due to this tendon profile, you will get, so stress is applied something like this. So due to this tendon profile, you will have movement like this. Okay. So here this beam will bend something like this. Okay. And on top of this neutral axis, it will be tension. And below the neutral axis, it will be compression. Okay. So at the support, the tendon is in the tension zone. So above the neutral axis is there. So at support, we will be taking minus. Okay, because our tendon eccentricity is in tension. It is above the neutral axis. So if you see here, it is above the neutral axis. So it is above the neutral axis at the support. Okay. So FC at support is equal to 6 minus 4.2. Here we'll take minus. It will be 1.8 Newton per mm square, and FC at center is equal to 6 plus 4.2, because here it will comes to at the center, the tendon will comes to below the neutral axis. So we'll take plus because it is in compression. So it is 10.2 Newton per mm square. Okay. So here you have two values. So you can find out the loss due to elastic shortening at support and at center separately as well, or else you can find out you can take the average of these two stresses at the support and at the center, and for that average value, you can calculate what is the loss of stress due to this elastic shortening. Okay. So one way of finding is you can find out the loss separately for this and for this one, for at support and at the center. And another thing is you can take the average of these two at the support and center, and for that average value, you can find out what is the loss due to elastic shortening. Okay. So we'll take average. And we'll find out the loss due to elastic shortening. Okay. So average stress in concrete. Okay. So here, let us try to understand how this stress distribution is there. So this is at support. This is the support, and let it be center. Okay. At support, you're having a stress of 1.8. And at center, you're having a stress of, this is 10.2. Okay, so this is 1.8. Okay. So the stress distribution is something like this. Okay, so we need to find out what is average of this value. Okay. So this is will be 1.8 here, and how much will be this one? So this will be, so from 10.2, if you subtract 1.8, so it will be 8.4. Okay. So this is this profile. This profile looks like a rectangle, right? So for rectangle, the CG will lies at one or here around two-third of 8.4, right? So somewhere here. So this is 2/3, right? So now let us find out what is average stress. So that is 1.8 plus two-third of 8.4. Two-third of 8.4. So it will be 7.4 Newton per mm square. Okay. So we got the average FC value. So this is FC average. Okay. Now loss due to elastic shortening in cable 1 is equal to, we know alpha E into FC average. Okay. Alpha E has given it is 6 and FC average is 7.4. So put these values in calculator, you'll get the value around 44.4 Newton per mm square. Okay. So did he ask to find out percentage? No, just he asked to find out what is the loss. Okay. So here is the loss due to elastic shortening in the cable 1, that is 44.4 Newton per mm square. Thank you.